Just a reminder to mute yourself if you aren't already. Okay, so can you all see my screen? Can anybody confirm?
Yeah, screen's visible.
Okay, cool. Okay, so morning everyone. I hope you're all well and rested after the IAU General Assembly. I'm very happy that I got to go down and meet some of you in person, but I'm possibly more happy that it's over now. It was a lot of fun, but a bit overwhelming. So I needed something to get me back into the mood of research. And so I think this lecture is coming at a good time. So what better way to get us back into the spirit of radio astronomy than a nice chat about radiative processes. So that's the mechanisms by which radio emission is produced in the universe. Before that, let's do a quick recap of what we talked about in the last lecture, which was all about radio signals. So we said that a radio telescope receives a signal, a radio wave from the sky, and digitizes it into a voltage, a time series of voltages, of complex voltages. And the power of the signal is given by the square of the amplitude of that voltage. And this power is related to the flux density of the source multiplied by the effective area of the telescope. The flux density is given by the integral of the intensity of the emission over solid angle and frequency. So if we assume thermal emission, then we can substitute a Planck spectrum in there, which is given by this equation. And then if we rearrange that for temperature, we have moved now from a voltage power into a brightness temperature. And we can define this brightness temperature even for non-thermal emission. And the use for doing that is because temperatures add linearly. So we can measure temperature with our telescope and decompose it into a linear sum of terms from different sources. So some of the temperatures come in from the source we're looking at, and then the other ones we can measure or model away. So for today, you should know two things. First, you should know how radio waves are produced by thermal, non-thermal, and spectral line emission processes. And then you should understand how each mechanism can tell us something different about astrophysical objects. So we like to divide emission mechanisms into two different categories, continuum emission and line emission. Continuum emission means that it is of a continuous range of frequencies, as you can see in the picture. Whereas line emission is just at a specific frequency, and that can be an emission or an absorption spectrum. So let's talk about continuum emission first. So that's emission that you see over a broad range of frequency. And this type of emission is typically caused by the acceleration of charged particle. So this is basic electrodynamics. If you have a charged particle and it undergoes some acceleration, then it releases a photon in the form of Bremsstrahlung. And the power of that photon will be given by this Larmor formula. So the power of the photon is related to the charge of the particle squared, and is proportional to the square of the acceleration of the particle. So, and we know that the photon energy is proportional to the frequency of the photon, right? So in other words, the frequency is related to the square of the acceleration. So if the higher frequency emission requires a more violent acceleration. Also, the fact that it's a continuum of radiation, so it's a continuum of frequencies, implies that we are talking about a population of particles. So it's not a single particle, it's a population of particles which each exists on a spectrum of energy. And then the different mechanisms for producing radio emission each correspond to a different way of moving the charged particle, of producing that acceleration. So the first distinction we have to talk about is about non-thermal versus thermal radiation. And that depends on whether the population of particles you're looking at are in local thermal equilibrium or not. So if you have a population of particles that are in thermal equilibrium, the only movement that is happening to those particles is because of random thermal oscillations and then collisions with one another. So we know that the particles, each one will have a specific kinetic energy associated with it because it's moving around. And the temperature of that population corresponds to the average kinetic energy. So the hotter the population, the faster they are moving around. So thermal radiation then is the radiation that you get just from the movement and the collisions of these particles. In order to get non-thermal radiation, you need some other source of acceleration beyond just the natural movement of these particles in free space. And so typically non-thermal radiation requires a magnetic field. So thermal emission, as we've said, comes from the movement of particles in a population of particles that are in thermal equilibrium. The Boltzmann relation tells us that the temperature of the particles is directly proportional to the average kinetic energy. And if we have thermal emission, we can assume that they have a black body spectrum, which is given by this equation, the Planck spectrum, which we talked about before. That's shown on the left here, sorry, on the right. And there are a few important features about it. Ven's displacement law tells us that the peak wavelength of that spectrum, so where the spectrum is peaking in wavelength, is inversely proportional to the temperature of the particles. So the higher the temperature of the particles, the lower the peak wavelength of that emission. And then we can also see that with increasing temperature, the area under the curve is also increasing. And so that corresponds to the power of this emission. So the Stefan Boltzmann law tells us that the power of the emission increases with temperature to the power 4. So increasing temperature dramatically increases the power of thermal emission. And then another important feature of this emission is that it's never polarized because there's no directionality to this emission. You don't see any polarization. If we change this plot on the right to have frequency on the x-axis instead of wavelength, we can plot it like this. And you can see the typical radio frequency is about 1 gigahertz, is all the way on the left there. So even for particles that are quite cold at room temperature, 300 Kelvin, their peak in the black body spectrum is way beyond what's typically accessible to radio telescopes. So the only way that we can see thermal emission from in the radio band is in two scenarios. Either you need a very low temperature, so it's all the way over here somewhere. And so that would typically be the 2.7 Kelvin cosmic microwave background or some cold interstellar dust. Or in some cases, if you have a very sensitive telescope, you can sometimes catch this Rayleigh-Jean's tail right at the edge of the spectrum. Right. So besides thermal emission coming from the movement of particles in thermal equilibrium, there's also emission coming from the interaction between those particles. And this is called free emission. It's also called thermal Bremsstrahlung. And specifically, it is emission that comes from the interaction between an electron and an ion. So in the diagram at the bottom here, you see there's an electron coming in on the left, and it's approaching a positive ion, noted by Z plus. The Z is the proton number. And because their charges are opposite, the electron and the proton are attracted to one another. So as the electron goes past the ion, it is attracted to the ion, and its path changes. It deflects, and that's an acceleration. And so, with any acceleration, a photon is emitted. And so, if the if the ion has a charge plus Z times E, then the acceleration that it experiences is that Z, the proton number, multiplied by E squared over mass of the electron R squared. So the higher the ion proton number, the heavier the ion, the greater the acceleration, and the higher the frequency of photon that will be emitted. A specific type of free emission is H2 emission. But to describe that, I have to get into a bit of a tangent about really annoying astronomy nomenclature. So in astronomy, so if we look at the interstellar gas, it's made up of a bunch of different elements. You have the most abundant element is neutral hydrogen, and it can be atomic or molecular. In radio astronomy, if it's atomic, we call the neutral hydrogen H1, where the 1 is a Greek numeral. If it's molecular, we call it H2, but the 2 is an Arabic numeral. Then we also get ionized hydrogen, so hydrogen which has lost its electron. And in that case, we call it H2 with Greek numerals. So if somebody is talking about H2, you first have to ask them, are you talking about molecular neutral hydrogen or ionized hydrogen? It's very annoying, but that's the notation that we have inherited and are stuck with. You also get a lot of helium in the interstellar gas, and that can also be neutral or ionized, and we use the same notation for that. And then there are trace elements of heavier elements. In astronomy, we call everything heavier than hydrogen or helium, we call it all metals, whether it's actually a metal or not. We typically see carbon, nitrogen, oxygen, neon, silicon, iron, and to an astronomer, all of those are metals. And those can be ionized as well, in which case we use the same notation with the Greek numerals, and they can either be double ionized or triple ionized, in which case you get carbon 3 or even carbon 4, for example. So the reason why we have this distinction is because it's useful for us to divide regions of the gas into H1 regions and H2 regions. H1 regions where the hydrogen is mostly neutral, and then H2 where it's heavily ionized. And the reason for that is because we can see those regions using different emission mechanisms. So H2 regions are ionized, and as we've already seen, when you have a lot of ions, that means that you can get H2 emission. Free emission. H1 regions are neutral, so you don't get much free emission, but instead we can see these from the 21 centimeter H1 line, which I will talk about a bit later. But H2 regions are typically found surrounding active galactic nuclei and in star-forming regions. So that's one of the big uses of studying H2 regions, is that they can tell you a lot about the environments where stars are being formed. So this is an example of an H2 region. This is a photograph of the Eagle Nebula, and these dark pillars, these clouds, are called the pillars of creation. And that's a very poetic name, but it reflects the fact that these are H2 regions. So there are clouds where there's a lot of stars being formed, kind of a cosmic nursery for stars. So H2 regions tend to give you very beautiful pictures because they kind of highlight these clouds of gas where stars are being formed. This is what the spectrum of free emission looks like on the right. It's a power law, meaning that it's a straight line on a log-log scale, but it is a power law that has a turnover. So the slope of the power law changes at about 1 gigahertz. If we look at high frequencies above 1 gigahertz, the slope is about negative 0.1. So it's very flat. And we call this the optically thin regime because that is the regime where emitted photons can easily escape the H2 region without being scattered. So the lower the frequency of the photon, the lower its energy, the more easily it is absorbed by the surrounding H2 region. And so once you get to a frequency below about 1 gigahertz, that photon is getting continuously absorbed and re-emitted by the particles before being able to escape. And in that case, the spectrum of the particle takes on a black body spectrum, which has a slope of about 2 in this regime. So by looking at the slope of a free emission spectrum, you can say already what the say something about the optical depth of that gas. So the density of the gas and other traits as well. So this is an example of a combined spectrum for a nearby starburst galaxy called M82. Starburst galaxy just means that there's a lot of star formation happening, so we expect to see free emission. And on the right, you can see that there's a very nearly black body spectrum from above like 100 gigahertz, which corresponds to the thermal emission from the gas in the galaxy. And then going down to lower frequencies at around 100 gigahertz, the free emission starts to take over. So here the spectrum of the free emission is given by that dashed line. And you can even see at around 1 gigahertz, you can start to see the turnover in that spectrum. And then towards lower frequencies, you get another emission mechanism take over, which is the synchrotron emission, which is a non-thermal emission mechanism, which I'll talk about a bit later. So let's talk about non-thermal emission. So thermal emission comes from the movement and interaction of free particles. In order to get non-thermal emission, you need acceleration from some mechanism, some source beyond that. And that typically most often involves a magnetic field. So at radio frequencies, the spectra are typically a black body, a power law spectrum. And we know that thermal emission in radio frequencies has an index of about +2. And at radio frequencies, free emission is about -0.1. And then non-thermal emission has a negative spectral index. So this is a very important rule of thumb to have in your brain. If you're looking at the spectrum of a source, if it is positive, very positive, approaching +2, it's probably thermal emission. If it's pretty flat, then it could be free emission. But anything negative, meaning that it gets weaker at higher frequencies, that is an indication that we have non-thermal processes occurring. So the first and most simple non-thermal emission mechanism is called cyclotron radiation. And that involves an electron spinning around a magnetic field line. So you have a magnetic field line, like in the picture here, and then an electron is rotating around that at a certain frequency. So the gyro frequency, which I'm not going to go into the maths of all of this. If you are interested in studying the stuff in detail and going through this from first principles, I do recommend that. And that you can read about that in pretty much any textbook on radiative processes. But I'll just give you the broad qualitative results here. The gyro frequency is given by the electron charge multiplied by the magnetic field strength divided by the electron mass. So the stronger the magnetic field, the faster that electron will spin around it. The cyclotron frequency, that is the frequency of the photon that will be emitted, is given by that gyro frequency divided by 2 pi, and that is about 3 × 10⁻³ multiplied by the magnetic field strength in Gauss, which gives you a value in gigahertz. So if we plug some numbers into there, a typical magnetic field in the interstellar medium is about a microgauss, which gives you a cyclotron frequency of about 3 Hertz. So that's a very low frequency. We're not going to be able to observe that with the radio telescope. But the sun has a magnetic field of about 300 Gauss, which gives you about 1 gigahertz cyclotron emission. So we can actually see quite clearly cyclotron radiation coming from the sun, but not from typical interstellar magnetic fields. More often than not in radio, instead of cyclotron radiation, we see synchrotron radiation. And that is very similar to cyclotron radiation, except that it involves ultra-relativistic particles instead of any old particles. So the particles are, the charged particles, typically electrons, are moving at close to the speed of light. And they're spinning around the magnetic field and releasing photons. But because of their relativistic motion, if the electrons are traveling in our direction, in our line of sight, that photon is blue shifted. It's Doppler shifted to a higher frequency, to a higher energy, and that can blue shift the emission from even a weak magnetic field source up into radio frequency. So that's why we tend to see synchrotron radiation more than cyclotron radiation. Another important effect now is that if we go back to the gyrofrequency equation, which is inversely dependent, proportional to the electron mass, but in a relativistic regime, we can't use the rest mass of the electron. We have to use the electron mass multiplied by the Lorentz factor. And the Lorentz factor is proportional, or is dependent on the speed of the electron. So the emission frequency that we get now doesn't just depend on the strength of the magnetic field, but it also depends on the energy of the emitting particle. Also, due to the fact that the magnetic fields are typically directional, they are in a specific direction, you will get synchrotron radiation that is typically polarized. Because the electrons are radiating these photons, they lose their energy. And so in order to sustain synchrotron radiation over a long period, you need to have a continuous supply of relativistic electrons. So a typical source of a synchrotron radiation includes supernova remnants, quasars, and active galactic nuclei. And each of these have a different way of producing relativistic electrons continuously. So, for example, I'm most familiar with pulsar emission, which is synchrotron radiation. And that comes about because the neutron star is spinning very rapidly and it has a strong magnetic field. And the rotation of the magnetic field induces an electric field which pulls charged particles out of the surface of the neutron star and then accelerates them along magnetic field lines. And so you have a continuous production of these charged particles being accelerated, and that's how you end up with synchrotron radiation. So let's look at the spectrum of synchrotron radiation. So we should remember with continuum emission that we are talking about a population of particles. It's not a single particle. We observe the aggregate result of the spectrums of each particle's output all aggregated together. So the spectrum of a single electron's synchrotron radiation is shown on the top right there. You get this peak in the spectrum, and the frequency where that peaks is dependent on the energy of the electron, or the Lorentz factor, the speed of the electron. So the higher energy electrons will produce a spectrum that peaks at a higher frequency. But then we have a whole population of these electrons, and each one will have a different speed. So if we look at the main plot here, you can see that there are lots of these peaked synchrotron spectra, each from an individual electron, and that the peak where the peak frequency depends on the electron's energy. And so when you put all of these together, the observed spectrum is the sum of these individual electron spectra, and that observed spectrum depends on the energy distribution of the seed electrons. In other words, if we have a population of electrons that have a power law distribution in their energy, then we will also see a power law distribution in the synchrotron spectrum. So the spectrum of the photons reflects the spectrum of the electrons. To give you an example, if we have a power law spectrum in the electron energy, so then you have the number of electrons with the specific energy, E, is proportional to the energy to the power minus P. So the P is the spectral index. Then we will get synchrotron radiation, which is also a power law, proportional to the frequency to the power alpha, where the alpha now, the index of the spectral of the synchrotron radiation is given by p minus 1 over 2. So if you have electrons with spectral index p, the photons will have spectral index p minus 1 over 2. So a typical photon synchrotron spectral index that we measure in the galaxy is about 0.75, which would imply that the electrons must have a power law with an index 2.5. So you might be wondering, we see as we see in the spectrum, it's a steep negative spectrum. But what happens at very low frequencies? Does this intensity of the synchrotron radiation keep increasing up into infinity to very low frequencies? That would be bad, right? We can't have infinite intensity. But fortunately, the universe has a way of regulating itself. And in this case, it does so using synchrotron self-absorption, which means that at very low frequencies, the spiraling electrons begin to reabsorb those low energy photons. So you have the electrons, and they are producing these photons, but the photons just get reabsorbed by the same electrons, and that's called synchrotron self-absorption. And again, this is an effect that depends on the optical depth of the electron population. So at high frequencies, the photons find it easy to escape from the electrons, so the optical depth is thin. So you have this power law with p minus 1 over 2 index. And then at lower frequencies, it's easier for that synchrotron radiation to be reabsorbed. And then we get the absorption by the electrons, and there's a turnover in the spectrum, and that it starts to take on a power law index of 5 over 2. Now, the exact frequency where this turnover happens depends on the optical depth. So in large part, it depends on how densely the electrons are packed together. So if you have a compact object, like a neutron star or active galactic nuclei, producing these radiation, the electrons are packed quite closely together, right? And that means that the turnover frequency can happen actually at quite high frequencies. So studying where this turnover happens can already tell you a lot about the environment where this radiation is occurring. Right, the next mechanism we have to talk about is called inverse Compton scattering. So regular Compton scattering is when you have a photon that strikes an electron, and the photon gives some energy to the electron. So the electron is energized by the photon. Inverse Compton is when the energies, so Compton scattering happens when the photon is more energetic than the electron. Inverse Compton happens when you have a low energy photon striking a relativistic electron. So now the electron has more energy than the photon, so the electron gives energy to the photon instead. So you have you start with a low energy photon and then you boost it up. We call it it's upscattered. And the frequency of the photon, of course, changes as well. So you start with a low frequency photon and then it's upscattered to higher energies. Related to that is a phenomenon called synchrotron self-Compton. So this happens in a lot of cases where you have relativistic electrons producing low energy photons via synchrotron radiation. And then those same electrons, the same relativistic electrons, can then Compton scatter the photons. So those electrons give their energy to the photons and boost the energy of the photons by a factor gamma squared, the Lorentz factor squared. So for a typical radio photon, you can have it be upscattered by a factor 10 to the power 8. So you can have radio photons scattered up into the tera-electron volt range, which is X-rays and gamma rays. So this mechanism is a crucial part of how we can explain seeing high energy emission from active galactic nuclei and pulsars, etc. You need this synchrotron self-Compton mechanism to get the highest energy photons that we observe from these sources. Right, so that's it for non-thermal processes. Let's move on to spectral line emission. So we know that atoms and molecules have quantized energy states. So the energy states have specific values. They can't have just any random energy. It has to be a specific value. And then as they move between those energy states, they will absorb and emit photons with the corresponding energy, or in other words, the corresponding frequency. So when we look at the radio spectrum of a source, there may be frequencies with increased or decreased intensity corresponding to those transitions. Those are called spectral lines. And we can measure the frequency, strength, width, and profile of these features to probe the density, temperature, and chemical composition of the emitting region. So the frequency of the spectral line emission depends on the kind of transition, energy transition that you are observing. So in a typical optical or UV regime, you tend to see transitions in the electron energy within an atom. So electrons in an atom go from high to low or low to high energy shells within the atom, and that produces photons, energetic photons, up into the electrical and optical and UV regimes. For infrared radiation, you typically see transitions involving vibrational states of molecules. So they have different vibrational states, and that can give you a transition corresponding to about 0.1 to 0.01 electron volt. In order to get radio emission, which is low energy, we typically see transitions involving rotational states of molecules. So for example, it's showing a carbon-oxygen molecule, and one rotational state might have a slightly different energy from the other, and radio waves are produced when the molecule shifts between those possible rotational states. And this means that spectral lines from radio in the radio regime tend to be probes of molecular gas. This is a list, an incomplete list of some of the important spectral lines that we see in the radio, less than about 1 terahertz. And you can see there's a huge amount of them, 76 in this list. So it would be impossible for me to go through even a small amount of these. So instead, I just want to focus on one specific one, which is number 2 on this list, which is the neutral hydrogen or H1 line at 1.4 gigahertz. So this is a very important emission line in radio astronomy. It's the line that comes from a neutral hydrogen atom. So in a neutral hydrogen atom, so it's neutral, meaning there's a proton and an electron. And those protons and electrons, they spin and induce a tiny magnetic field that interact with each other. And the total energy of the atom is very slightly greater when the spins of the proton and electron are in the same direction compared to if they're in opposite direction. It's a very small energy difference, only about 6 micro electron volts. And don't ask me where that comes from. It's a result of some quantum effects. And the corresponding photon wavelength is 21 centimeter, or about 1.4 gigahertz. Now, this transition is very unlikely to occur naturally, so it has to be induced by collisions in H1 gas. So this H1 line is tracing the dynamics of H1 regions of molecular gas, of hydrogen gas specifically. So in an ISM gas, this for a given atom, this transition only happens about once every 200 years. But that's for a single atom. Hydrogen is the most abundant element in the universe by far. So even though it's fairly rare, for a single atom, overall this happens all of the time, and this emission line is can be seen everywhere where there's hydrogen. So that is the main use of this H1 line, is because of its how ubiquitous it is. It allows you to trace processes at all sorts of different places where hydrogen gas is observed. So I drew up a list of some uses that we have that I've come across for the H1 line. These are just random, more or less, uses of a H1 line that I have come across. Very likely there's a whole range of more uses for H1. Just want to give you some idea of the things we can do with it. One thing we can do is to measure the Doppler shift of the H1 at various points in an extended emission. So, for example, if you're looking at a galaxy, that galaxy is moving around. There's dynamics happening within the galaxy as it's moving, and those different velocities of the galaxy will impart a Doppler shift onto the H1 line. So if you have a part of the galaxy that's moving towards us, that will blue shift the H1 line. If there's a part of the galaxy that's moving away, it will red shift it. So by looking at the way that these H1 lines within the galaxy are being Doppler shifted, we can effectively measure the velocity of those components of those regions, and so get an idea for the dynamics of the galaxy, which can give you some insight into the formation of these kinds of objects. Another thing that you can do is to measure the Doppler shift of H1 within the Milky Way, so the local galaxy, and then if you know the distance to certain objects, you can use this measurement of the H1 to construct a galactic rotation curve. So that's the speed of the rotation of the Milky Way as a function of radial distance from the center. And then you can use that rotation curve along with an H1 measurement at a given point in order to measure distances within the galaxy. So that can give you an independent measurement of the distances to different objects within the galaxy. You can also use the total line flux, which is the flux of the emission line integrated over its width, and it can give you an estimate for the total hydrogen mass in the galaxy, and you can then use that to estimate the mass of the total mass of that galaxy. We can also observe the Zeeman effect, and that's the result of magnetic fields that split the H1 line up into multiple components. So it splits the line into different frequencies as a result of some quantum effect. And by observing that Zeeman splitting, we can measure the strength of the magnetic field. So you can build up a picture of how strong the interstellar magnetic field is at different regions. And then also you can use it for cosmology, in particular to study the dark ages of the universe before reionization. So in some of its early stages, the universe consisted mostly of neutral hydrogen before it was ionized again later to form galaxies and stars. And so you can use the emission line from those at those very high redshifts to study how the universe looked in those very early days. And then the final emission mechanism that I want to describe is maser emission. And there are a lot of people in this group who study masers for a living, and so I'm more familiar with them than I am. So allow me to just give you a very simple picture of them. And yeah, so masers is an acronym. It stands for microwave amplification by the stimulated emission of radiation. So it's a microwave analog to a laser. So laser is optical, maser is microwave. And the operating principle there is we know that each type of atom or molecule emits and absorbs specific wavelength. So if you have some cloud of gas consisting of a certain atom or molecule, as you can see in the picture, if you have a background source which shines some electromagnetic radiation onto that cloud, and if it contains the correct wavelength, then that correct wavelength will stimulate the emission of more photons with the same wavelength. So you get so there's an incident wave. If it has the right wavelength, you get more photons with the same wavelength. And then those photons can go on to stimulate more emission of photons with the same wavelength. So you have a cascade effect where the intensity of the line keeps increasing, increasing, and increasing. And so you get very bright emission lines in this way. So in order to get this effect, you need to for the energy of the particles in the maser to move from a low energy state, shown by E1 here, to a high energy state E2. That's called population inversion. And the frequency of the maser emission is proportional to the gap between those energies. So for radio emission, which is low frequency, that gap is quite small. So as we've seen, for example, for H1, the gap between the emission states is pretty tiny. So so population inversion in radio regimes actually can happen relatively easily. You just need some background emission, which could be any emission really, and then a pumping mechanism that helps you to get that inversion. And this pump can be a radiative or collisional. Those are different models depending on which process is dominant in the pump. So that's about the extent of my knowledge about this stuff. I'm sure other people will be more familiar with exactly how these pumping mechanisms work. So let me just give you a few examples of some common maser lines. You get hydroxyl masers, OH, silicon oxide, water, methanol, ammonia, and formaldehyde. Those are the most common ones. And then some features is that the lines tend to be very narrow, less than 1 kilometers per second. And they come from compact regions, so it's not an extended region of the sky. It's coming from some compact cloud of gas. And the brightness temperature also tends to be very high, up to about 10 to the power 10 Kelvin. The emission tends to be polarized, probably because of the presence of magnetic fields in the gas. And then the maser emission is also typically associated with star-forming regions. So I know that's one of the major uses of studying masers, is to try to trace where star formation is happening in the universe, and try to understand um, the processes by which stars and galaxies are formed. And then some masers I know are periodic, on the order of 10 to 100 days. And as far as I know, that periodicity is still up for debate as to what is the cause of the periodicity. So that's it for today. Let me just leave you with a summary. So we have, broadly speaking, two different kinds of emission: continuum emission and spectral emission. Continuum emission means over a broad range of frequencies, and that can be thermal emission from the cosmic microwave background or cold interstellar dust. You can get free emission from H2 regions, or synchrotron radiation wherever charged particles are accelerated. For example, radio galaxies, supernovae, pulsars, AGN. Then there's spectral line emission. In radio astronomy, the most prevalent one is the H1 line, which traces a neutral hydrogen gas. Then you can have some molecular rotation lines, which is due to the change in rotational states in cold molecular gas. And then there is also maser emission, which amplifies molecular emission lines in dense and warm molecular gas. So that's it for me. Let's move on to any questions.
Hi, Dr. Tian. Thank you for the wonderful lecture. I have some questions on the chats.
Yes. Okay. So the questions, let me see. At lower frequencies, does the synchrotron emission dominate the free emission? Yeah. So let's go back to this plot. So you can see a typical free emission, because it's so flat, towards lower frequencies below about 10 gigahertz. Free emission is very much dominated by synchrotron radiation. So synchrotron is very steep negative, so it goes up very high as you go to low frequencies. And then, is a spectral index of 1 thermal or non-thermal? So I don't believe you should be able to see a spectral index of 1 in a typical situation. So in radio waves, the typical index for thermal emission is positive 2. And then, so you should, if it's thermal emission, it should be about positive 2. And then free is about 0, and non-thermal is about negative. So I don't think you should be able to get 1. And then, how does the density of the electrons influence the peak of the spectrum? So I assume you mean in synchrotron radiation, in this spectrum here. Is that right, Rahul?
Yes, that's correct.
Yeah. So the density of the electrons, the more dense the electrons are packed together, the higher the optical density, the optical depth that the photon will experience. So optical depth tells you how easy is it for the photon to escape the electrons, basically. and that is dependent on the frequency or the energy of the photon. So a high energy photon with high frequency more easily escapes the electrons, so it's optically thin. As you go down in frequency, um, lower frequency photons more easily get absorbed, so the optical depth begins to increase. So the peak of the spectrum um, depends on the optical depth. So if the density of the electrons are greater, then the optical depth will be uh, higher as well, because there's more electrons, there's more of a chance that they absorb the photon. And so the peak of this spectrum will shift to higher frequencies. Does that make sense?
Yes, yes, it does. But I also want to know: does the electron oscillations, does the electron vibrations also influence the opacity of the medium?
The electron vibrations, do you mean the gyro frequency of the electrons?
Yes. So the motion of the electrons, does it also have an impact on the opacity? So if electrons are moving
Mm,
very fast, does it mean it
it's
has a higher
a,
opacity?
it's a good question. I can't remember my plasma physics well enough to remember exactly what um, determines the optical depth of the electron population. Um, yeah, you'd have to go back to the maths on that one. Unfortunately, I can't remember. Okay. There's a
Thank you, sir.
question from No problem. There's a question from Portia on the chat. As the electrons begin to reabsorb the low energy electrons, I mean the low energy photons, does this mean that as time progresses, the peak of the spectrum shifts to lower frequencies? So we're talking about um, synchrotron self-absorption. So the electrons absorb the low energy photons. Does this mean that as time progresses, the peak of the spectrum shifts to lower frequencies? So that depends on if there is a steady supply of relativistic electrons. So if you have a source that keeps producing these relativistic electrons, so the density of the electrons stays the same, then the peak is going to stay uh, uh, at the same place. But if the source can't keep up that acceleration, then you're right that the electrons are going to start losing uh, their energy, and then the peak is going to shift. But for the most part, in AGN and pulsars and so on, there's a pretty steady supply of relativistic electrons. That answers your question. Jifar asks, can we identify the region of free spectrum depending on their frequency? So, um, let's see. So this is what the spectrum looks like. Depending on the frequency, the slope is going to change, which tells you about the optical opacity, optical depth of the source. So you might be able to um, identify something about if you know the structure of a galaxy, where H1, where it should be optically thick and where it should be optically thin. Maybe you can say something, but in general, the frequency is just going to yeah, tell you about what the spectrum looks like. Hope that makes some sense. I don't think there's anything that we can directly say about the region where it's coming from just based on the frequency. If anybody has a better answer, they're welcome. Paul, I see your hand is up.
Yeah, mine was related, my question is related to what you're talking about. So we know for the H1 regions, the neutral hydrogen, you're looking at the 21 centimeter line. But what do you look for to look for H2, so ionized hydrogen?
Yeah, so ionized hydrogen, sorry, go ahead.
No, just because it's looked at frequently.
Yeah, so then you're going to be seeing free emission. So you're going to look at, for a continuum emission specifically, sorry, in the region sort of below the thermal frequencies. So if you look at the spectrum of the source and you see that there's a tail towards low frequencies, an upturn, that's probably an indication that there's free emission happening as well.
So specifically, if you want to identify an H2 region, you are looking for, we'd look at the spectral index.
I believe that's the case, yes.
So I've heard it now, you hear it quite often in terms of, no, this is an H2 region. Just curious in terms of how it's identified, but
yeah,
it does seem like it's just looking at the spectral index and confirming it's free emission.
I think so, yeah.
Okay, thank you.
Okay, anything else? And again, I do recommend everybody, this is all a very much a qualitative overview. If you are interested in using this for your own work, it is very much recommended that you go through the maths yourself, and from first principles. That will help you a lot. Okay, I'll give one more chance for questions. Yeah, very much you're welcome. Let's see, let me quickly, sorry, I don't have yes, here's the lesson plan. So in 2 weeks, we will have another lecture about positional astronomy. So that's a fun one. It's basically trying to deal
Hi,
with all of...
sorry, sir. There's a
Yes.
question on the chat by Paul.
Oh, sorry, Ampo, I didn't see that. Okay, let's deal with that first. So if a population of relativistic electrons have to be reproduced to maintain synchrotron emission over long distances due to their loss in mass, it's loss in energy, what then is the mechanism with protons, which are unlikely to lose a lot of mass? So protons are also charged particles, right? So they can also move around, rotate around magnetic fields. But because their mass is so much higher than electrons, the gyro frequency, the speed at which they rotate around that magnetic field line, is very slow compared to an electron. And the frequency of the photon that we get out is proportional to the speed at which it's rotating. So for a photon, any rotation is going to give you a photon that's very, very low frequency. So we can't see any, in the radio regime, we can't see any radio emission coming from photons because the gyro frequency is just too low. So when we're talking about synchrotron radiation, we're really just talking about electrons and sometimes positrons. Does that make sense?
Makes sense.
Cool. So next week is positional astronomy. We're going to try to help you to understand all of the different coordinate systems that we use in astronomy, which for me personally was a big headache trying to understand the stuff. So yeah, I hope that's useful, and I'll upload this to YouTube, and yeah, see you all in 2 weeks.
Well, thanks, Tian. Much appreciated.
Of course. Okay.
Thank you
Thanks
so
a lot,
much.
Tian.
Okay. Thank
Cheers.
you. Cheers. See you all.
Thank you.
Bye bye.
Bye.